Thanks for the introduction. On my side, I didn't quite hear the audio, but I guess that's fine.
I hope so.
Yeah, your mic was a bit far away. But thanks for the introduction, and I'd like to share with you my recent work with Peter Rode at University Technology of Sydney on this general framework for the composition of quantum homomorphic encryption and quantum error correction. So the context of this research is like the task that we are interested in to address is that of secure delegated computation. So in this scenario, you, the client, you have a quantum input, and you want to have have a quantum computation be performed on this quantum input. However, quantum computation is very expensive, so you would delegate this computation to some server, like some company, and they will compute on your quantum input. However, you don't really trust the server. I mean, because you have really sensitive information, so you would like to encrypt the quantum input. So the server is going to compute on the encrypted quantum input. And after that, after the server does the computation, it will send back the quantum state to you, the client, and you will decrypt the information. And hopefully at the end of the day, you will receive the correct computed output. And of course, what I've talked about is delegated computation, but I have not talked about security or privacy. So there are two notions of privacy at play here. So on one hand, you want to keep your information safe, well, secret from the server. And this is what's known as data privacy. And the server sometimes also wants to keep the computation secret from you. So because maybe it has some proprietary algorithm, it doesn't want to let you know what it's doing. So that's circuit privacy. So however, for today, we're going to focus on schemes with just good data privacy. So in fact, we do not discuss circuit privacy. So so you can think of the computation that is to be performed as a difficult computation, but is known to the public. Everyone knows what is supposed to be done. Okay, but the client just wants to keep the information secret from the server. And when we're discussing data privacy, there are two types of notions where this security can arise. The first is from computational assumptions, which is the most mainstream method. So basically, for quantum homomorphic encryption schemes, usually they would use classical homomorphic encryption as a black box for which computational hardness assumptions would apply to them. And because they use this classical homomorphic encryption black box with computational assumptions, so the corresponding quantum homomorphic encryption scheme will also require these computational hardness assumptions. So there's one wide sector of literature that focuses on like, you know, computational hardness assumptions. But the stronger form of you know, security is from information-theoretic reasoning. Basically, you don't want to assume that some computational task is hard. You just want it to be information and theoretically secure. Problem with this, of course, although it's a gold standard, but because you're asking for a lot, so perhaps the computational tasks that you can do with this information theoretic security will become less than that for computational hardness assumptions. And in this talk, we're going to focus on the second type of data privacy. So data privacy from information-theoretic setting. Of course, I haven't defined what it means, but you just need to be patient while I lay down the problem. So now I can start to discuss what is quantum homomorphic encryption. So quantum homomorphic encryption is basically describes a specific type of secure delegated quantum computation where you have this client and server, and basically the client is going to first encrypt the state row with a key kappa. And so basically this encryption map is just a quantum channel. It's a quantum channel which is labeled by the index kappa, the key. And because the client, you're not going to tell the server what your key is. And let's say that the set of your keys is capital K, which is a finite set. So the server would assume that you're picking your keys like uniformly at random. So the server would see the encrypted state not as the left side, but as the right side, like as a highly mixed state. And ideally, you would like the right side to be like, for example, a maximally mixed state. So no matter what the input row is, and that would be like the gold standard for security, because then the server would never find out what quantum inputs you have. Okay. So after the client has encrypted the stuff, then there's this computation, which is a quantum channel from a set of allowed channels. I use this A to denote the set of allowed channels that denote the computation. And this quantum homomorphic encryption, I mean, there's this word homomorphic. So the question is like, what's homomorphic? So the thing that's homomorphic is the computation has to obey a homomorphism. So basically, if you, the client, is going to perform like C1 and C2 on row, I mean, if you could do C1 and C2 on the row without the encryption, then what you would like to have is that there's a homomorphism that takes the C's to a different space, such that this homomorphism applies. And these homomorphisms will act on the encrypted states. And it's cumbersome to write this map every time. So we can use the notation with the bar to denote that the homomorphism, this group homomorphism, has applied. So okay, so you can think of group homomorphisms if you demand that the set A is a group under composition of the C's. And of course, at the end of the day, the client is going to do some decryption, and this decryption is a quantum channel. It will depend on the secret key, and in general, it may also depend on the computation that's being performed. Okay, of course, the idea is that the decryption map should not be harder to perform than the actual computation. Otherwise, the client can do it himself. So there's going to be some requirement on the complexity of the decryption algorithm, so that this cryptographic task makes sense. So you want this you want to impose some constraint such that the decryption channel is easy to do. Okay. And so now there are some requirements of quantum homomorphic encryption. I mean, so the idea is that if the client does like some computation on the unencrypted state, it should somehow map to like the computation on the encrypted space. But sometimes you need to put an additional CK so that for this thing to apply. And the requirement that we need is that we like to have is that this CK is also an element of the allowed set of computations, so that things are nice. But in the special case, in which a CK is the identity map, then basically you can have this very pleasing identity over here. Okay, all right. And the requirements of decryption is also easy. So for example, you can consider the case in which you do no computation, right? So so in that case, we can denote the decryption map of the case where there's no computation to be performed as just labeled by just one subscript, the key. And of course, we would want, you know, if you decrypt after you encrypt, it should be just the identity channel. This makes total sense. So and it's also clear that if the encryption channel is a unitary channel, then obviously you can pick the decryption channel to be the corresponding inverse unitary channel. And this is exactly what we are going to be restricting ourselves to today. So we're going to restrict our attention to encryption maps that are unitary channels. Okay. So so for a cryptographic scheme to be meaningful, it has to be correct. That means that it needs to give the right output. So for example, what you want is that after you encrypt and then you do a computation and you decrypt, then you should get you know, the correct computation. And it is easy to see that as long as you define the decryption map to be given by this thing over here, then this equation 11 applies. And basically, you just use the requirements that I showed you on the previous slide, and it basically just pops out really easily. I will not bore you with the details, but it's really easy. It's a pictorial proof. All right. So now I can talk about slightly more formally about what are the properties of a quantum homomorphic encryption scheme. So, well, the most important property that we are focusing on today is the so-called data privacy, which we define to be the maximum trace distance between the any two encrypted states where you pick the states within some allowed set of states. Okay. All right. And so you say that the scheme is epsilon secure if this, well, delta is at least epsilon. And of course, you want it to be correct. Basically, you want this to always hold. I mean, you want the correct output. Yeah, this is quite a tautology. And also, oh, well, this is the important restriction that you want the decryption map to be easy. So basically, you want the circuit complexity of decryption channel to be at most a polynomial in key length. This may seem like a bit of a weird requirement, but it's used in the literature, and it helps to keep the complexity of the decryption channel, you know, within well, reasonable. And over here, key length, like what's key length? So usually you can think of so for example, you can think of the key as being represented by bits. And if you do that, then the key length would just be like the log of the number of keys that you have. Okay. So because eventually we want to discuss quantum homomorphic encryption with quantum error correction. So we need to be able to put different homomorphic encryption schemes together to get a new, bigger homomorphic encryption scheme. So basically, we want to compose quantum homomorphic encryption schemes. So we can define what it means formally. By the way, if there are any questions, you guys can ask. So so now I'm just spamming you with like some symbols over here, right? But the idea is very simple. The idea is that, well, I'm going to define a quantum homomorphic encryption scheme to just be like some tuple of things that we care about. Okay, the first thing we care about is like the set of input states, which I denote by this supercalligraphic S. And then you also need the set of keys. Makes sense because you're going to encrypt. You need a set of keys. And then you also need a set of allowed computations that you're going to care about. And of course, you need the homomorphism, verify. And you also need the set of all the encryption maps. Well, I denote the set of all encryption maps to be, well, the set of all encryption kappa. Okay, so this makes sense. I mean, you're just writing down all the requirements of all the things that you need to define a quantum homomorphic encryption scheme, which I've talked about earlier. So this makes sense. Okay, so then, so you can call this Q. So this tuple, you can call it Q. And then you can consider schemes like Q1 to Qm. And then you just like call them formally as this additional tuples over here. So then we're going to define what it means that you can compose you know, the schemes Q1 to Qm into a bigger QHE scheme. So you know, this is not the only way to define. I mean, but it's just a particular way to do the definition. So and we try to do the definition in as a natural and easier way as possible. So we're going to require that the encryption map of the composed channel is going to be just like you know, the encryption maps applied independently on each piece, which makes total sense. And then of course, if you do this, then the set of your encryption keys is going to be like it's going to be the tuple kappa 1 to kappa m. Makes sense. And then okay, so now we've talked about encryption. Now we need to talk about like, okay, what about the computations? So are the computations just going to be tensor products? Of course we could do that, but then it wouldn't be as interesting. So for example, if you have a bunch of schemes that each of which can do some Cliffords, and then if you say that you know, the composed scheme can only do like Cliffords on their own quantum wire, it seems to be like not very meaningful, because then what about entangling operations between the schemes? So we require that the set of computations can have some entangling operation here, which makes sense. And then yeah, which makes sense. So so this is just a natural definition. Oh, I realized I forgot the math script here. All right. And then, of course, so now we've defined the computations. Then we also need the homomorphism property to hold. We want the homomorphisms. We need there to exist a homomorphism that works. And we need the new homomorphism. Okay, so this is like just what it means to be a homomorphic encryption scheme. It doesn't And then, of course, we need to be able to determine the security from the security of the previous schemes, of the previous homomorphic encryption schemes. However, I've not told you what this function f is. So, I mean, it just needs to exist some f. But of course, calculating this may be hard. I mean, there, in fact, in most cases, there always exists such a f. So this is, you can think of it as a tautology. And of course, it needs to be correct and compact. All right, so I've really told you like the bare minimum definition of what it means to be able to compose the schemes. And then there's this theorem here that basically the point of this theorem is just to tell you how you can make the decryption map of the quantum homomorphic encryption scheme given like all of the properties that I laid out earlier. So basically, we just need there to be some commutation properties. Did something happen? You're not seeing me. Let me try to so I was kicked out of the presenting mode. Let me just try to click on the link again.
Okay.
Hi guys.
Hey.
You hear me?
Yes.
Okay, thanks for staying. Let me share the screen. Yeah, so basically we just require this. So if this commutation property holds, then we'll be able to write down explicitly what the decryption map is. And well, this is also easy to show. So basically, we now know how we can what the framework for composed schemes is. It's really easy if you have all of these properties laid out. Of course, this is all at a very abstract level. And the idea of how you're going to show what the decryption map is that you just write down all of the properties that you have, and then you just play around, and eventually you get it. Okay. Okay. So now is the well, the main part of the talk, and which is quantum error correction. So there are two. So the question is, how do you put quantum error correction together with quantum homomorphic encryption? So there are two ideas. First of all, first idea is that you can put the quantum data into QEC code before you encrypt, or you can encrypt first before encoding it in the code. So over here, I'm using encode and encrypt in two ways. I mean, in different ways. So encode is going to refer to putting it in a quantum error correction code, and encrypt means put it in a QHE scheme. Okay. So so in the next part, we're going to show give some conditions where these two approaches are equivalent. And when these two approaches are equivalent, it makes understanding of it makes things nice. Okay, so basically the idea is that now you know that you're going to have like some you're going to put some QHE schemes together. So you have some Q1 to QQ and the Q tutors. So you have the normal Q schemes and the Q tutor schemes, and you're going to put them together. And the idea is that all of the Qs without the tildes are going to hold, for example, the quantum data. And the Q tutors is going to hold like no information. So then you can put it in the code later. So of course, we need to define what we mean by code in this framework. So the idea is that you think of, so in quantum error correction, if you want to do a computation, you'd have to do some logical operators. And these logical operators are just like homomorphisms. So if you have, before you put it in an error correction code, you have like C2 and C1. Well, the logical, what a logical operation does is that it's a homomorphism that takes these channels to new channels, and in such a way that this, well, homomorphism holds. So that's what logical operators do. They're homomorphism. So everything's homomorphic, nice and homomorphic. So and also this the logical operators have this nice commutation properties. Like, so you can commute the encoding map. If you commute the encoding map past the computations, then you get the logical computations. And similarly, if you have the encrypted operations over here and the encrypted encoding thing, you also want the same algebraic properties to hold. So so this is the idea. Everything is homomorphism. So so now the question is, okay, so So what we like to show is that we want to show that there's a way to imagine encoding after encrypting to be, in some sense, equivalent to encrypting after encoding. And of course, when you do this on the left side, if you use like some key over here on the left, the key on the right, it may become like how to say it? It may become different. So it will become different in general. But then we just need there to exist some key for it to work. And this is just this lemma. Well, I mean, I put it as a lemma because this is really easy to show given all of these properties that I've shown here. I mean, everything just works out. And the requirement is very mild because all that you need is that you need this encryption map to obey this relationship. I just realized I forgot some superscripts here, but that's fine. But you get the main idea. I'll just skip this. All right, so we've completed the most very abstract and formal part of the talk, where we talk about this framework for composing QEC with QHE. And the main take-home message is that, well, it's really easy if all of the properties that we've written down, they actually hold. And then, of course, the question is, all right, so are there any interesting schemes for which these properties would hold? And I'm going to say yes. And there are two notable examples over here, although in the paper I gave an additional example for bosonic codes. So the first example is a trivial, what I call Pauli-key encodings. Basically, you have a quantum state. Let's say you have an n-qubit state, and then the client has an n-qubit state. And basically, the way you're going to encrypt it is you're going to apply like a one-time pad. Basically, you're going to apply n-qubit Pauli at random, uniformly at random. And if you do that, the server is going to see a maximally mixed state. And if you do that, then what the server can do is like some Cliffords. And because Cliffords have nice computation with Pauli's, then you can have a trivial scheme that can support some Clifford computations. And of course, if you want to throw in some magic states in, I mean, if you want to do some T gates, then things get tricky. But the idea is that you can throw in some magic states. I mean, you can use gate teleportation to enable some T gates to be performed. But the problem with that is that it increases the decoding complexity. So you're going to at most be able to do a polynomial number of T gates in the first scheme. And similarly with the second scheme, which I'm going to talk about a bit more. So in the second scheme, the encryption operation is even simpler than the Pauli-key encryption scheme. So in the Pauli-key encryption scheme, you actually need to apply like the Pauli's on the quantum state. But for the idea of permutation, if you want to use a permutation key, all you need to do is you just need to permute the qubits you have. And what this amounts to, like operationally, is that you just need to like rewire your quantum circuits. Of course, some people think you may need to do a bunch of swaps, but then you can also just physically move your qubits around. And if you just move your qubits around, that's a completely classical process. Or maybe you don't move your qubits around. You just like relabel them. You just change the labels on the qubits. Okay, so this is how the permutation key encoding works. So you begin with like some lattice over here. So over here, each circle represents 1 qubit, and you are going to encode. You have 1 qubit of information that you want to put in a, quantum homomorphic encryption scheme with quantum error correction. So the first step is you're going to, so this green one has the information, but all these gray ones, they're all maximally mixed states. So what you're going to do is you're going to apply a quantum channel on the first column and put it in like some code. Well, this code, yeah, you're going to put it in this code over here. And oh, yeah. So you're going to put it in this code. So I forgot. So actually, these on the first column over here, these are the exception. These are not maximally mixed. They can have like some. You can assume these to be zeros. So this will be a quantum error correction code. And then next you apply like some encoding map across some of the rows, and this and the process of this quantum channel, unitary quantum channel, doing it horizontally, what it does is that it puts it into a random code. So like row-wise is like the quantum error correction code. Column-wise, this puts it into like the quantum homomorphic encryption scheme. So in this picture, what you're doing first is you're putting it in a quantum error correction code first, and then putting it in a quantum homomorphic encryption scheme. But as I've mentioned before, in some cases you can see these two processes can be interchanged. So you could have also applied this quantum homomorphic encryption thing first, and then you apply the QEC encoding later. You would also be able to do it. But in this case, I applied QEC's encoding first. So after this, the information is spread on this block over here, and then what the permutation key does is just shuffles the columns around, and it was shown. It was and the security of this scheme has been is easy to show because the security of this scheme has been shown for the version without the quantum error correction code, like with just one row. So you would we are able to easily determine the security of the composed schemes with extra rows. So of course, now the question is, what's the computational model? We can definitely support Clifford operations. So the Clifford operations are going to be like, if you want to do a logical X, you're just going to apply like X on every single qubit over here. Like logical Pauli, you just apply the Pauli on every single qubit here. And this is because the code that spreads it across column-wise and row-wise is a transversal code that applies the Pauli identically and independently. So that's nice. Okay. And also, when you apply these Paulis on the maximally mixed states, it does nothing. So it doesn't change those guys. So you don't really need to know where the columns are. You just apply the Paulis everywhere for the logical Paulis. And for the logical Cliffords, you just apply them the same, like single qubit Cliffords, you apply them everywhere. And you just need some mild condition on the numbers. The number of, you just need this to be the number of columns -1 to be divisible by 4, which is a mild condition, mild technical condition. And you can also do like C0s transversally. But of course, the question is like, if you want to do a reasonable quantum computation, you want to do some T-gates. So with that, we need some classical back and forth communication. Otherwise, if there's no classical back and forth communication, which means that the scheme stays as a quantum homomorphic encryption scheme where there's only one round of information going from the client to the server and back. In that case, then we need an exponential number of resource states to do like the gate teleportation thing. which is not ideal. But if the client and the server, if you and the server can just ping information back and forth, then you can do a polynomial number of T gates, which is all right. But then the next question is, but what if errors occur, and can you do things fault tolerantly? And the answer is yes, because you can just use the fault tolerant code over here, and then of course, the larger the code you use, the worse the security is going to be. And so the question is, what is the trade-off between the error correction ability and the security you're going to have? And use, for example, some existing fault-tolerant schemes and do some high-level analysis. So, for example, we can consider using a family of surface codes where the length of the code is like the square, scales as the square of the number of errors it's supposed to correct, that it can correct for sure. And you assume like some base physical error probability of 10 to the minus 6, and you say that you want the logical failure probability to be really tiny, like 10 to the minus 30, because you like that for nice quantum computation. And then you assume that this logical failure probability scales as like as some function of t, like the number of errors that you can correct over here, and you assume further that you know what this constant is. If you assume these things, which you can pick from the literature, like from some of their numerical heuristic examples, then you will be able to determine the performance of the quantum homomorphic encryption scheme. So then, of course, what is the performance of a quantum homomorphic encryption scheme? You can say, well, it's the number of T gates that you can do, like let the number of T gates that you can do be like R. Yes. And so if you want to do like say 100 T gates, and you want your security to be like really tiny, I mean, like you want the data privacy to be really good, then you need like 10 to the 24 qubits total for the scheme. So I mean, what this shows is that, well, yes, we can in principle do fault tolerant delegated computation, but it's going to require quite a number of resources. Of course, these numbers are going to improve if you can improve like the base error rate. But I just pick this base error rate to reflect what seems to be like reasonable in current near term. Well, what's reasonable in maybe the next few years. So what this suggests is that we're probably not anywhere close to having this fault tolerant secure delegated computation yet. I mean, unless if you can have 10 to the 20 something qubits. So with that, oh yes, and so this kind of concludes my talk today. I'm happy to discuss more, but I conclude with this setting, like the setting in which we are imagining is that the client can do like very limited stuff, and basically there's lots of resources, like some factories of Bell states that you can send to the client and the server. And with these resources, you can actually do, if this exists, architecture exists, then this type of security task can be done. All right, so I'm happy to take any questions. Thanks for listening.
you can hear me?
Yes, yes, with the mic close to your mouth. Yes.
Well, thank you very much for your talk. For example, if the audience has any questions, that was a good time.
Maybe I ask simple questions.
Yeah.
Yeah. Thank you for the nice talk. I just want to get the intuitive feeling. What's the purpose of the homomorphism here? I mean, are you trying to make the things more hard to be?
So the purpose of the homomorphism is to make the construction of the computations more natural for the server. So for example, if the client already knows like the gate decomposition that should be performed, then if the homomorphism holds, then the server can just do the corresponding version with the same gate decomposition, but with the homomorphism applied on each gate. So the server doesn't have to work too hard. But of course, if the server is all powerful, this is not a necessary requirement. So yes, so I mean it's a nice requirement, but then there are schemes studied where this homomorphism property doesn't apply in delegated computation, but it just makes things harder.
Yes. So then I understand the purpose is to make it easier to manipulate for the server
Yes.
side, but how about the privacy? I mean, where can you improve the privacy in the setting?
So there are two notions of privacy: data privacy and circuit privacy. So perhaps you're asking about circuit privacy. Is that right?
Actually, your setting is for data privacy, right?
Yes,
So
for
I'm
data
asking,
privacy.
yeah.
So for data privacy, there have been a number of schemes that have been studied, and is, for example, the permutation-key scheme. The data privacy, so the epsilon, it basically scales like as like 2 to the minus the number of columns. So basically, as you increase the number of columns, the data privacy improves exponentially. However, the data privacy also decreases as you increase the number of rows. So the data privacy gets worse linearly with the number of rows in the scheme. So so this corresponds to the number of qubits that you want to work with.
So can you explain the scheme? I mean, the different row means different scheme and different column means different more state qubit.
Okay,
Is that right?
so in the base scheme, right? So you have the quantum homomorphic encryption scheme is going to apply like across the column. So it's going horizontally. So so if you have a qubit here and you use the QHE way to encrypt it, then the trace distance is going to be like exponentially suppressed in the number of columns. Then if you have more and more qubits, like on each of the different rows, each of which holds a different secret, then the game is that you want to the secrets to remain, all of the secrets to remain secure, but then the data privacy is going to get worse with as the number of secrets increases. Here that each secret is 1 qubit, right? So over here, so intuitively, the number of rows corresponds to the amount of quantum is corresponds to the size of your quantum input. the number of qubits in your quantum input. So the number of rows is the number of qubits in your quantum input.
Yes, and different color represent for the quantum error correction, right? Is for the purpose.
So the gray, most of the gray stuff is all maximally mixed states. So it's the maximally mixed states are there to make it hard for the server to determine what the secret is, because the intuition is that once you permute this circle over here randomly, then it's hard for the server to guess which where this circle is, and the server is going to permute the columns. No, the client is going to permute the columns, and the server will find it very hard to guess which column holds the information. But in order for it to be hard, the encryption needs to take the secret from the first column to like half the number of columns, so that to guess the right permutation is really hard, because then the number of permutations, the number of ways to choose, like half the number of ways to choose, like n over 2 out of n, is like exponential in n.
Yeah, I see.
So the number of rows in the super vanilla scheme with no quantum error correction, each row represents a different like quantum input. So so what I'm saying is that the quantum input, this vanilla scheme can be taken into a quantum error correction setting by just using some of the rows to put it into a quantum error correction code.
Okay, and how about scheme? I mean, you apply M scheme, and then what's the scheme here?
All right. So your question is, what if you don't apply my suggested permutation-key encryption scheme, and you apply your favorite scheme? You just apply like some channel randomly, right?
Yeah.
Okay. So if you do that, you can also analyze and get like some security parameter, but then most likely, because you picked it like in a very poor way, the security is going to be horrible. So what we want the security, so we want this what we would like is, okay, we like this parameter, this epsilon, to be exponentially suppressed in like say some like in the number of qubits that you use for the quantum homomorphic encryption scheme. So yes, so you want the security, you want this trace distance to approach 0 in an exponential way. So if you pick a scheme randomly, as I did in the early days, before I found the nice scheme, I could only get like say like a approaching 0 polynomially, which is lousy, because if it approaches 0 polynomially, then you might as well have not done any encryption and just repeatedly sent the scheme, and then you will achieve a similar performance. Kind of.
Yeah, yes, sounds good. But can you explain what's the trick of the scheme here? I mean, are they entangled, or why it get the improvement?
Oh, what? Okay, so yes. So this permutation-key encryption scheme, which is not the, which is it gets is nice well, security from the fact that you're using a highly random code. So if you trace out any single column over here, if you trace out any single column after you've done the encryption, and the remaining states will become maximally mixed. This corresponds to the fact that the code, when you're doing the encryption, because you are encrypting it across like a lot of maximally mixed like gauge qubits, then you essentially get a very random code. And in fact, you can imagine this very random code to be like randomized over all stabilizer codes that support transversal Clifford gates. and because it's so random, it has a distance of 1. It can do no error correction. So once you trace out a single qubit, it becomes maximally mixed state. So this is the intuition. So that's why you need a lot of maximally mixed states here before you do a unitary encryption encoding. You know, that's the intuition. And this permutation encryption scheme was discussed in my earlier paper, not this paper, but an earlier paper which I referenced a number of years ago.
So the maximally entangled state is the key ingredient or is the necessary?
So there's no maximally entangled state here. In this picture, is a lot of maximally mixed states.
Okay.
So the idea is it's very easy to prepare this. You just prepare this maximally mixed state, but they need to be genuine maximally mixed states. They cannot be secretly entangled with some adversary.
Okay.
So in the security model, I'm considering these are genuine maximally mixed states. Of course, if they are maximally entangled, secretly maximally entangled with some adversary, then my scheme is vulnerable.
I see. Okay. Yeah, clever. Thank you.
Thanks.
All right. Do we have more questions? I think perhaps not. So let me thank you again for having me here and the talk.
Yeah. Thank you so much for the invitation, and thanks for listening.
Yeah, thank you very much.